Hello, my name is Matt Holliday and welcome back to my class. For this segment, what I'd like to do is talk about formatted and file I/O. Now, we've seen a little bit of that in the example program, so I just want to go a bit more into the functions of printf and also how to read files from the command line. Okay, so I want to start by talking about standard I/O. I've mentioned it before, and that is Unix has the notion of three streams of standard I/O: standard input, output, and standard error output, and they can be redirected separately. And almost all modern programming languages expose the same three things to you somehow, and Go does. Through the OS package, we have the variables like os.standardin. And we've already seen those. I can do a fump.println and it goes by default to standard output, but if I use fprintline, then I can direct it to os.standarderror, which is the standard error output. And in reality, what we have are a family of functions. And I'm going to show they have a couple dimensions. So first of all, we have println, and println just takes whatever you give it, some variable number of arguments, and puts them onto one line together, usually with spaces in between them. And then we have printf, which is similar, but the first argument is a format string, and that format string allows us to say how do we want the other things to be formatted, to be represented as text. And of course, this goes all the way back to C. This is basically a C concept that's also shown in languages like C++. A lot of languages have something like this for formatting strings and formatted I/O. But there's a family of these functions. So we have println and printf, and then we have, if we put f in front of them, we have fprintln and fprintf. And they just allow us to give an output identifier like os.standarderror, so we can direct it to standard error output instead of the regular standard output. But then there's a third family of functions where we put s in front, so we have sprintln or sprintf, and they actually don't do I/O at all. Instead, they do exactly the same logic about formatting the output, but they return it to your program in a string that you can use in some other way. Now on this slide, I've got a bunch of format codes, and this is not all of the format codes, and no, you don't have to memorize them. I just want to point out the kind of the range of things that's in there. So we have some format codes for strings and characters, and a way to quote characters automatically. And then we have some format strings for numbers. We can show them as decimal numbers, we can show them as hexadecimal, we can also have a way to do floating point numbers. And we'll see in a second that allows us to control, for example, how many digits show up. There's a %t that can print booleans, and they print out as either true or false. And then we have a couple of things I've shown before. There's the %T, which prints the type, and %v. Now %v is neat because it'll print anything that's capable of being represented in a Go program can be formatted by %v in some meaningful, readable way. And I'm going to go through a whole bunch of examples because I want to show how those are really useful for debugging your program. And we'll see them again and again. And then the other thing I'll point out is if you actually need to print a %sign, then you have to put two %signs in a row. So there's a bunch of Godoc out there for the FUMPed package. And I really recommend you look at that because it talks about the formatting verbs and also the various things you can do with them. I'm going to show a few examples. I've already shown one interesting thing, the brackets around a number that allow you to reuse a parameter in another place. And I'll show that to you again. The pound in front of %v. So if you have %pound_v, the pound is a modifier that basically says, well, get fancier. And so all of that stuff is written up in the Godoc for the FUMP package. Okay, so I want to switch over to the playground and demonstrate some of these things, show a bunch of the formatting strings and work through them. So I'm going to start off with creating some numbers. I want some integers, and we'll also have a couple of floating point numbers. Okay, and we're going to print them in different formats. So all the printfs, of course, they start with a string. So what do just A and B look like as numbers? And the answer is, okay. We'll come back to C and D in a sec. Okay, they just show up as digits, and they take as many places as they need. Okay. Now there's another character we can use instead of %d, because sometimes I want to see these in base 16 or hexadecimal. And so I can use %x and do that. If the %x is a lowercase x, then numbers like, okay, the new lines, when you do printf, you got to remember to put in your own new lines. They're not there automatically. We'll run that again, and now we get something like this. Okay, the %x will print the ABC in lowercase x if the x in the format string is lowercase. And if I change that to an uppercase, then those numbers will print out with an uppercase A, B, or C, or whatever. Okay, now I can go one step beyond that. And here's where our friendly pound sign comes in again, because if I put a pound in front of the x, it's going to very usefully put the 0x in front of the hexadecimal number, which allows us to print them out in a way more like they would show up in code, and we can clearly see that is not just any old character, it's a hexadecimal 0x and some hexadecimal number characters, digits. Okay, so again, this is one of the uses of the pound sign. And now we'll come back and bring back our floating point numbers. Okay, so when we print a floating point number, we use %f, for example, and Go will give it a number of digits, usually 6 digits after the decimal point, which may not be convenient. And we can control that by giving the f character right here, the f verb, our own decimal point and say decimal 2, meaning 2 digits after the decimal point. And so we see that 3.45 just prints the 45. Okay, I could increase that from 2 to 3, and then it would print 3.450, for example. So we can tell it how many decimal digits to have after the decimal point. Okay, so I'm going to put a print line in here just to sort of give some space, and we'll move on and do a few other things, because I want to show the concept of using columns right? So these vertical bars in the format string, they're going to print out as literal vertical bars. But what I want to do is I want to format numbers. I'm using them to show the column size. I'm going to put a digit here in front of the %d, or in front of the d verb. And what that does is say, print this number in a column that is the width of 6 characters. And so when I run that, it's going to come out below this on a line of its own. And we can see down here, right, the vertical bars are just there to help illustrate the columns. You don't have to have those. Okay, I'm going to get rid of all of this out of the way. And let's keep on doing that, because I want to show the next thing, which is if I put a leading 0 and have %06d, it will format those with leading zeros. So instead of right justifying in the column with spaces, it's going to right justify by writing in some extra zeros. You may need that, you may not. More interesting is, what if I want to left justify? And so I'm going to take the 0 and change it to a minus sign. So it's %-6d. And now we'll see that the numbers are all left justified in the column, and the spaces go afterwards. Okay, so actually the first and the third example are probably the most useful. Now, let's try doing that with our floating point numbers. So we'll uncomment C and D again. And we need to change these to F. Now, what I can do is I can give a %6F, or I can do like 6.2. So 6.2 says, well, print it in 6 columns with 2 of those columns representing the numbers after the decimal digit. Now, it may not produce quite what you think. And the reason for that is, although the second number, the 3.45, well, that requires 4 spaces, right? 3.45, because we only allowed 2 decimal digits after the decimal point. But the other number, we just said 6F. And we said, well, how many decimal points is up to you, Go? You use as many as you want. And it says 6. And that means it needs 8 column spaces to print the number because it's not going to truncate. And so it's not going to fit into 6 columns. So when you put the number 6 here, what you're really doing is you're saying use at least 6 columns. But if you need a bigger space, and we would see this also, what happens if I make my 3, 4, 5 into a big number? Okay, well that also doesn't fit. So it doesn't fit in 6 columns. It's a bigger number than that, and it's just going to take up whatever space it needs in order to print that. So the way around that is you really have to know, what range of numbers are you going to get? And I could change these 6s to 9s, for example. And if I did that, now everything's going to line up. Right? So now I'm saying do everything in 9 columns of 9, and now the 1.20 fits in there because all those 1.20000, so whatever, fit into the 9 columns. Okay, so that just gives you an idea about some of the ability to use modifiers on the verbs to show different things in the output. I want to now go back to the %v and %t and go through some different examples that'll show how useful those are for debugging. So I'm going to reset my playground. And we're going to start off with a slice. So S is going to be a slice. And we'll just give it the values 1, 2, 3. Okay. Now I want to point out something, and that is there's a format button up here. And if I press the format button, it will put the program into standard format. Okay. So it added those spaces that were missing inside there because that's the way Go programs are normally formatted. And now I want to do some printfs. And I'm going to start off by remembering to put in my new line explicitly. All right. So we're going to look at the type of S. And then I want to look at the value of S, and then I want to look at the %pound_v, sort of the more fancier version of the format of S. And let's see what those look like when they print out. Okay, so it's a slice event, and it's represented, the type is represented by the empty square brackets and int, because that's the same way that we write it when we declare it in the program. Okay, if I print it out with %v, what I get are a pair of square brackets and the actual numbers. They don't have commas in them, so it's not quite like JSON where you'd expect to see commas between the numbers. All right, you just get the square brackets and the values in order with spaces in between them. But if I do %pound_v, what I actually get is a combination of type and value. And in fact, here it looks it looks like the same thing that I declared in the code. So %pound_v is going to get you close to an output that actually looks like the way you would type it in your code as the type and the value. All right, so having done that for a slice, let's move on and do that for an array. So I'm going to create an array. Of course, I have to give it a number. And in this case, I'm going to go to array of runes. So these are going to be the characters A, character B, character C, right? Remember, characters use single quotes. Okay, and we're going to do the exact same thing down here, except we're going to do it with A instead of S. My typing skills, again, are not very good in front of a camera. I don't know what it is. The camera does something to my fingers and I can't type. All right, so we'll run that and we get slightly different output. Now, I'm going to, just because there's not a lot of space on here, I'm going to get rid of the S part and we'll just look at the A part. All right, so let me run that again. There's no way, unfortunately, on the playground to change how much space is available at the bottom for the console. It's one inconvenience, but we can live with it, right? And what do we get? Well, we get, it says it's an array of 3 int32s. So remember, rune is just an alias for int32, and it just goes back to showing the int32 as the base type, because that's a Unicode code point. It takes a 32-bit integer to represent a Unicode code point. Now, if I print it out as with %v, what I get then are the numbers. These are the integer values of those three characters. That's not terribly convenient, and so I'm going to add one thing in here. Okay, I'm going to change that to %q. Now, %q, typically you use that on a string, and it prints the string with quote marks. But in this case, it's going to change the approach to printing that list of characters. The %q comes out as square brackets and the characters quoted. So we can see that those are actually the characters A, B, and C. And that's a lot more useful. And then the third form of this, the %pound_v, is going to show us, again, the combination of the type and the value, right? Again, the type is going to have a base type of int32, and the values are going to be the numbers, not the characters. And I don't think that there's a way to change this to show the characters instead of the numbers. So it doesn't exactly look like what I typed in my program. Okay, so we've done that for an array, we've done that for a slice. Let's do it for a map. So I'm going to change my map, or change my variable here, to be a map of string to int. And we're just going to give it a couple of values in a map literal. And now we're going to ask the same question about the map. Well, except there's no, I'm not going to use %q. I don't think it'll do anything interesting, right? So what will my map look like with these three verbs? And we'll run that. Okay, so the first thing is I get the type, again, map of string to int. It looks the same as the program. My map down here, when I use %v, it has the square brackets, but it puts map in front of it to show it's a map and not an array. And then for each entry in the map, it has the key colon the value. Okay, again, it doesn't look like JSON because it's not quoting the keys or anything. And it doesn't put any commas in there either. You just get this display. And then the third thing, again, the %pound_v looks very much like what I typed in my code. Okay, so there's some other things I could print out, but those are the most common ones. I do want to point out one important thing. So let me do one more. I'm going to do one more example because I want to show a string. Okay. And first what I'm going to do is use these same things I've used already. Okay, so we'll run this, and of course it's a string, and it has the value a string, and notice that the %q puts the quote marks around it, the %v does not, but the %pound_v again goes back and puts the quote marks around it because that's how I typed it in the code. So %pound_v again attempts to show things the way they look in the code as much as possible. Now, I'm going to do something here, and that is, what if it's a bunch of bytes? Okay. So very often we do things like I open a network connection and I get a bunch of bytes back that have JSON in them, right? But if they're a slice of bytes, the bytes of the string are going to print out as numbers, okay? And that's not very convenient. So I'm just pointing that out to you so you remember if you're looking at a byte slice, again, you're literally going to get square brackets and a bunch of numbers in there representing ideally characters. And what you're going to want to do then is make sure you convert it back to a string so that you actually get the string output. Okay? You're going to bump into that a number of times where I have a byte slice that really represents a string, but again, it's a byte slice, and Go is not going to magically turn it into a string just because what's in it is legible text. You have to turn it back into legible text by casting it to a string. Okay, so I want to talk a little bit about using file I/O, right, where we're actually going to open files and read from them. Okay. in order to do that, there's various packages, and this slide just summarizes some of the key packages you should go look at. Of course, package OS has in it things like os.standardin and os.standardout. It also has the functions like create and open. So to do things on files as a whole with the operating system, you use the OS package to make a file or maybe even delete a file. Okay. Package IO has some routines for doing input and output, and buff IO has buffered input and output, and we've seen that already. And then we have a very convenient thing called IO/IOUtil, which has in it some utilities, some additional utilities to like read an entire file in one shot or write an entire file in one shot. And we'll see those. And then the last thing you're going to want to look at is a package called string convert. And that has utilities that can parse numbers from text. So let's suppose I've got a file. Now there's a library in Go for reading CSV. But let's suppose it wasn't there and I wanted to read CSV text. And maybe I have a column in the CSV that has floating point numbers. Well, I would go to string convert and use a function called parse float. And the parse float would know how to read the text that makes up a floating point number, interpret it correctly, and give me an actual floating point number in Go. Okay, so there's things in there to parse booleans and parse ints and parse floats and so on. And it's extremely useful and safe. That's the proper way to try to get numbers, for example, back and forth between text. Okay, so I'm going to jump into Replit again because, of course, if I want to do file I/O, I can't do that in the playground. So I'm going to go into Replit, pardon me, and I'm going to write a program that works sort of like Unix cat. And to do that, I'm going to need to import some packages again. So we'll just go ahead and start there. Okay. Now, so what I'm going to want to do, if you look at cat, and we're not going to reproduce all the functions of cat, but the most basic one is, for example, you can type cat and then you can type some files, and it will read each file and dump them together into standard out. So that's a way, for example, to actually take several files and put them together into one file, because you can take the output then and redirect that to another file that becomes the concatenation of the inputs. And that's what we're going to do here. Right, and again, so I'm going to look at os.args because that has the command line arguments, and we're going to treat them as file names. And of course, I'm going to ignore 0 because 0 is the name of the program. Okay, and I'm going to create a file each time through this loop. So I'm going to call os.open on the fname, on the file name, and it's going to give me back a couple of values: a file, some object that represents a file, and a possible error. And we need to check the error, right? We need to do something useful if the error is not nil. In this particular case, I'm just going to print the error on standard output. Standard error output. And then I'm going to continue, all right, and the assumption that, well, okay, that file's bad, but I'll read the next file, maybe it's good. That's a choice. I could also just kill the program and say, hey, you gave me a bad file, I'm just going to stop, I'm not going to go on. So that's a choice. I can either kill the program or I can continue. In this case, we'll just try continuing. So the next thing I want to do is, now that the file is open, I can do something with it. And I'm going to use a routine out of IO called io.copy. Right. And io.copy is a great utility because it's smart. It knows how to buffer, it knows how to read the input in chunks and write it back out in chunks in an efficient way. It doesn't try to read like the entire file into memory, and it also doesn't try to read like one character at a time. So it's going to do something efficient underneath. So we'll call io.copy, and all it does is it takes whatever's in file and puts it on the target, which here is os.standardout, which is actually another file. Okay. And again, if something goes wrong, I'm just going to print the error and continue. And now I need to do one more thing, and that is I need to close the file before I go on. Okay, I don't know how many files could be on the command line, but most operating systems have a limit on how many files you can open at one time in a program. And so every time we open a file, when we're done with it, we want to be good citizens and close it up so that we don't hit any limits. Okay, so this is my entire program. It should be my entire program to do this one simple function. Now, if you look over here on the left, I have already created several little text files that I can use for this exercise. And so I should just be able to go run dot. Now, if I do go run dot, there's nothing on the command line at all. Oops. And it's telling me I forgot to pick up IO. Okay, so I used IO.copy. I have to import IO. So let's try that again. And nothing comes out because nothing went in, right? This loop never did anything because there weren't any more command line arguments. There weren't any file names on the command line. So I could run it instead with 1, right? And it will copy whatever is in a.text and output it. All right, now, this is not very convenient because a.text didn't have a new line in it. And so I didn't get a new line when it printed the output, which is fine. We don't want to add any new lines that weren't there. But I'm just going to go through these real quick and add a new line so when I do them on the command line, they don't look funny. So we'll go back to main.go. Let's try that again. And this time it prints out, here is a line of text. And because that file had a new line in it, we get a new line on the console. Okay. It's just awkward if you don't have those extra new lines. Now I can also do a glob and just say all the text files, star.text, and it's going to print the text of each one of those one at a time and be done. So that's our little cat program. Right? We looped over the file names on the command line and we just read them from the file to standard out. So the standard out has all of those. And of course we could have redirected that. All right, so if I put a little redirection on there, nothing shows up on the console. But now if I go and look at d.text, it actually has all of the text from A and B and C in it, right? And we're done. So I want to go back to the slide for just a second and point out something. Again, we've seen this already. I can have a short declaration in my if, and I can check it, and we need to check it. So a lot of these files are going to return errors, a lot of these file operations. And this is a very typical declaration. If you go look at open, right? So open took the name of the file, which is actually a path, right? It could have slashes in it and so on. And it returns two things. It returns a file pointer and an error, okay? And it's a pretty standard convention in Go that if your function is going to return an error, the error is the last thing that it returns if it returns multiple things. And Go allows a function to return multiple values all at once. We'll see that more when we talk about functions. So this is why we do it with errors, because the function can return the file, and I don't have to worry about, oh, okay, so maybe the file is a null pointer, that's a special case, or the file is -1 or something. The file is the file pointer, and the error is a separate variable returned at the same time. Okay. Now, what's critically important is that we check and handle that error. If we think back about the internet has had enormous numbers of security problems, and that is the internet was programmed in C, and a lot of that stuff was built at a time when people were very cavalier about ignoring the return codes from functions or ignoring the length of an array. You know, how many things do I read in? Does it read past the end of the array? Okay. All security problems are bugs, and pretty much all bugs are potential security problems. So anytime that we ignore these error codes and just proceed on saying, yes, I'm sure it's going to work, we're actually opening up a hole in our program that eventually it's going to fail nastily, or it's going to provide somebody a way of attacking our program as a security hole. Okay, so we get error codes. The way Go does error handling, we'll talk about this more later, is to return explicit errors as a type. Okay, right now we're pretending that this type is either nil or not. It's a little more complicated, it's a little more interesting, but right now it's just something we can print, and we're showing that. We're printing those errors and then doing something, either continuing or quitting the program. But we're always checking them. Okay, so I lied. I've had 1 or 2 examples where, for the purpose of demonstrating in the class, I've used an underscore to skip the error. But in a real program, I would never do that. And ideally in a real program also, I would have static analysis tools that would help me find cases where I didn't check the error and point those out to me so I can fix them. Because from my point of view, those are bugs. Okay, so we're going to go back to Replit and we're going to build one more thing. Actually, we're going to build two things. I'm going to write a short program that will calculate a file size. And I want to demonstrate how we can do that in a way that's simple but not that great, just as a way of demonstrating some more things. And then I'm going to do it in a better way to show the difference. So I'm going to take my same program. Now this program right now is the cat program that's copying. And I'm not going to do that. Instead what I'm going to do is come down here and use IOUtil. All right, and so instead of importing IO, I'm now going to have to import IO/IOUtil. And in IOUtil, I'm going to use a function called readAll. And I'm doing this so I can kind of point out what's in IOUtil. IOUtil has this function readAll, and what it's going to do, I can't ignore that anymore. So I'm going to need to pull this out. Okay. The copy function, I ignored a value that came back, which is just the number of bytes copied. But now readAll is going to return actually the data, and I don't want to ignore that. So I'm going to put that into a variable, and if there's an error, I'll deal with it. And then I'm just going to print out the length of the data. Okay, so what does readAll do? If I look at readAll, okay, I don't know why it says it's an invalid, probably because we haven't run the function yet. Okay, but readAll is a function. Will it pull up the text? No, I got to build it at least once to do that. So let's go ahead and run it. Let's see what happens. Okay, it comes back and it reads all 4 files and tells us, and maybe now because it's built once, yeah, now it's going to load the Go doc for readAll, maybe. All right, well, it's very slow, but readAll is a function that returns a slice of bytes and an error. Okay, it may eventually pop up on here if we wait long enough. And I'm capturing that slice of bytes because that's what is a file in Unix, right? The standard concept of Unix is just a run of bytes as a file, which was one of the big contributions of Unix, because before that, all files were considered to have all sorts of weird structures that you had to deal with. And Unix had this notion, no, every file is just a file of bytes, so I can read the entire file at once with readAll. It gives me back a big byte slice. Now, that's simple if the files are small, and it's very convenient. If files can be arbitrarily large, I could get back a really big byte slice. And I really don't want a 1 terabyte byte slice in my program. In fact, my program's probably going to crash because I just don't have enough memory for that. So this is a simple example. I'm going to read through the files and I'm going to calculate the length by reading the whole thing in. It's just a demonstration of IOUtil. But I don't really want to write the program this way. Finally, Replit is going to show me the Go doc for the function, right? And so if I look at the Go doc for a function, readAll, it takes something that can read from, and I'm not going to explain that yet, and returns a slice of byte and an error, and that's what I did here. Okay, whoop. I got my byte slice, which was the data, I got my error, I checked and handled my error, and then I came down here and just calculated the length of the data and printed it out. Okay, so we're going to do one more of these. And what I want to do now is I'm going to gut part of this. Okay, we're not going to do this readAll thing. Okay, so I'm not going to use IOUtil. I'm going to need some other things instead. Right, we're going to bring back our favorite buff.io because that's a more convenient way to read files. And I'm also going to need something out of strings here in a minute, so I'll go ahead and pull that in. What I want to do is I'm going to produce a utility that does sort of what the WC program does in Unix. And WC stands for word count. Now actually by default, WC will print out how many lines, how many words, and how many characters. And we're going to do that here real quick. So I'm going to need some variables, right? And they can just be integers. And again, this is an example where, you know, in some languages, if I were doing this in C and I needed to deal with big files, I might be forced to call those things unsigned ints. Because signed integers, half of the bit space is used for negative numbers, and I can't have files with negative lines. But because these are 64-bit ints, they're so big, I just don't care. And so again, the default type for numbers in Go is just a plain signed integer, right? And of course, these variables will be 0 every time I open a new file because they're inside the for loop. So I start a file, I get new LCWCCC at 0 that I'm now going to do something with them. So I'm going to open my file just like before. That part doesn't change. But now I'm going to create a scanner, and we've seen this before. Right? And with my scanner, I'm going to have a scan loop just like before. So, and by default, this will be called one time for every line. That's convenient because the first thing I want to do is count lines, right? And so now every time I go through this loop, I can just increment LC, and that's going to count the number of lines, right? Now the text of the line, again, was scan.text. And so my character count is just going to be adding up. I just take the length of the text and I increment, if you will, or that's not the word I want, but I'm going to do a plus equals, and I'm going to add the length of the text into that variable. So now words are a little bit trickier because my scan.scan is producing lines, right? But turns out there's a useful utility, right? And the useful utility is strings.fields s. Now if I call strings.fields, do I get godoc? Yes, I do. Godoc says fields is a function that takes a string and returns a slice of string. And what it's actually doing is it's using the standard definition of space, which could be a space or a tab or whatever, and breaking it into words. So what I get back is actually a slice of strings, but it's a slice of the words. And all I've got to do then is calculate the length of that slice and again, add those into my ongoing WC, right? So WC picks up an additional number of words, CC picks up an additional number of characters, LC goes up by 1. And that just leaves me one more thing I've got to do, which is actually to print it out. So I'm going to use printf because I'm going to format this so it looks just like the real WC, right? And I'm going to print out the line count, the word count, the character count, and the name of the file, right? So I should be able to run this again. I think I'm good here. So if I run this on my text files, well, we'll just run it on one, right? And it comes back and says there's one line, 6 words, 22 characters in the file a.text. Okay, what if I do that for all of the files? So I'll just glob this, all right, and it gives me an output for each of them. And hopefully D, which was just the summary of the other ones, is in fact, if I add them all up, if I add A, B, and C, I get D. Hopefully that's true, it looks true. Okay, now let's compare that to the actual WC. So I'm going to call the Unix WC utility, and it's going to do something like that, but it's also going to add a total line. And we didn't do that, so I'm going to leave that as an exercise. And WC also has some options. It can print out only the line count. So it can say, hey, just the lines, don't give me the characters. And so here we go, we get one line in each except D, which had 3 lines. So WC takes some options, and WC, if you give it more than one file, right, if I just do WC a.text, it just gives me a.text. But when I did WC and globbed all the text files, it gave me one more line, which was the total. So I'm going to let you, as an exercise, figure out how to calculate the total or how to show just lines and not the other values by taking an option. Okay, I will actually come back at some point and show a command line option in a program, but it's something also, if you want to, you could go out and figure out how to do it now yourself. All right, so the purpose of this was just to show the I/O primitives. Okay, so I'm done with this segment. I wanted to bring out some things about formatted I/O and file I/O just to give you sort of a starting place for how to think about how to do command line programs.